Now, we talked about the transient distribution in the sense that those are the distributions that depend on time. What is the distribution after this many days, for instance? Then we will also talk about what we call the stationary distribution, and these will be the distribution after a long time for different initial distributions. Okay, what is long here? I mean, sufficiently long that you will see the same random behavior. Okay, observe for this specific example, even if you change the initial distribution, this means you start from sunny, this means you start from cloudy, this means you start from rainy, this means you start with equal probabilities. These are the two distributions we have seen in the previous example, etc. If you compute the distribution after 20 days, well, 20 is arbitrary here. I have just chosen it because it was sufficient. The 20 itself is not important here. It's just sufficiently long that the behavior becomes stationary. Okay? In a sense, it loses its time dependence. You see, all of these are the same. Okay? Whichever state you start from, with whichever distribution your initial distribution is, after a long time, you see there is a convergence to what we call a stationary distribution. In fact, if you disregard the initial distribution, if you just compute p to the power 20, what is the 20-step transition probability matrix? You see that all the rows converge to the same distribution. And this is not a coincidence. We will see why this is the case. And essentially, stationary distribution is, well, unlike transient distributions, it does not depend on time. It should not depend on time. That is the definition of stationary. Okay? Now, by definition, this is when time loses its effect. So we see this behavior at n goes to infinity. Okay? So this we call the steady state as opposed to transient behavior. So the Markov chain has a dynamic and you start it at some initial state and then it makes some transitions, but after a while it becomes steady. Not in the sense that it goes into a state and stays there. That's not it. But you see, what I mean here is the time share it spends in each state converges. So it's sort of like the law of large numbers. After a certain amount of time, the probability to observe each state converges to some stationary distribution. So this is expressed as the limit as n goes to infinity of pi n and pi n plus 1. Remember, these are the distributions after n transitions, and this is a distribution after n plus 1 transition. So in steady state, these distributions converge to some fixed distribution. But recall that, well, since these are apart by one transition, I can just write pi n plus 1 equals, well, I have a mistake here. This should be just pi n times p, because this is, well, one transition. Okay? Therefore, if you take the limit as n goes to infinity, this will converge to the stationary distribution. This will converge to the steady distribution. Therefore, in steady state, okay, you will have this relationship. Therefore, we say that a distribution pi, okay, where, well, it's a distribution, so it adds up to 1, is a stationary distribution of the discrete Markov chain with one-step transition probability matrix P if it satisfies the equation pi times P equals pi, okay? And in fact, if you look at our example, this distribution, which we have seen in the previous slide, this distribution actually satisfies this equation, pi times P equals pi, okay? Now let's see some examples, a very simple Markov chains. Let's see this Markov chain, you see how it behaves is you have two states, and every transition is certain to be to the other state. So it's sort of an oscillating Markov chain. Okay, if you are in state one, next time you will definitely be in state two, and the time after that you will definitely be back to state number one. So that means your one-step transition probability matrix is given like this, okay, from 1 to 2, from 2 to 1, etc. So if you write this equation, pi times p equals pi, well, pi is pi 1, pi 2, a two-element vector. If you plug in this equation, you will have, well, if you compute this, multiply this with this, you get pi 2, multiply this with this, you get pi 1. So that means pi 1 equals pi 2, and you get the same from this equation. You need one equation more to solve this, and that is the fact that the sum of these two must add up to 1. And since they are equal, they are both 1/2. Okay, which makes sense because, well, if you are in 1, you definitely go to 2. If you are in 2, you definitely go to 1. So in the long run, half of the time, this Markov chain will be in state number 1, and half of the time it will be in state number 2. It makes sense. Let's see another example. And here you see we have in state 1 a loop with 0.5, but with 0.5 it goes to state 2. And in state 2, what happens is curious. With probability 1, it stays at 2. So that means when the Markov chain is in state 2, it does not leave state 2. It stays there forever. Okay? So if you write the transition matrix, it's 0.5, 0.5 in the first row because you see with 50% probability it stays in state 1, but with 50% probability it goes to state 2. And in state number 2, it doesn't leave state 2. Okay? So with probability 1, it stays in state 2. Okay? So if you start this Markov chain in state 2, it will never visit state number 1. On the other hand, if you start it in state number 1, it will loop into itself a number of times, like Bernoulli trials, okay? And then it will move on to state number 2 and stay there forever. And if you write the equation, again, pi times p equals pi, here, this is p matrix. If you compute this product, this is pi 1 over 2. And this with this is pi 1 over 2 plus pi 2. You see, pi 1 and pi 1 over 2 equals each other, which means pi 1 must be 0. Okay? And since that is 0, pi 2 equals pi 2, obviously. Since you need another equation here, that comes from the fact that this is a distribution, so pi 1 plus pi 2 must be equal to 1, and therefore pi 2 must be 1. And this is, again, not surprising. Why? Well, you know that eventually, even if you start from 1, it will make a transition to state 2 and stay there. So in the long run, you will observe this Markov chain always in state 2. Okay? The third example, here we have transitions from both states to each other, and we also have probabilities, non-zero probabilities of staying in the same state. So our one-step transition probability matrix is given here. If you write the equation pi equals pi times p, this is the p matrix. If you compute the first element here, that is pi 1 over 2 plus 2 pi 2 plus 3. And the second component here, pi 1 times 1/2 plus pi 2 times 1/3. Okay? And this is equal to this. So this one equals pi 1, and this one equals pi 2. And at the same time, of course, pi 1 plus pi 2 equals 1. Well, you can either use a computer to solve this, or you can just write, let's say, pi 2 equals 1 minus pi 1, and plug that in here, and then solve pi 1. Or you can do that with the same in here, and you will see that the solution is 4 over 7, 3 over 7. Okay? And that means the probability that this Markov chain spans in state number one is 4 by 7 in the long run, and the probability that it will be in this state is 3 by 7. So in other words, this means when you observe this Markov chain after a sufficiently long period of time, the probability that you will see state 1 is 4 by 7, and the probability that you will see it in state 2 is 3 by 7.